by the WPA. So part of the construction they did in the area as works projects, a lot of the dams in the area were constructed at the same time. But you're traveling up the Mount Scott granite here, almost exclusively. The road stays on the Mount Scott granite. You can't see it, but there's a contact with an underlying gabbro underneath the mountain that the road skirts on top of. You can see it from the distance, so as you were approaching it, maybe you noticed that there was a tree line. We'll see that same tree line feature over to the west as well, so that'll come out again as we look at it. But this is the Mount Scott granite. There was a beautiful, what I've been calling a rock glacier, others call a rock glacier or a rock fall that's down the valley there. Look for it on the way out if you didn't see it on the way in. It's really close to the entrance, and it's a stunning example of these boulder fields that cover really just this eastern end of the Mount Scott. You don't see them further west, and I couldn't find an example further west. Am I wrong about that, Charles? But really, the only place you see these boulder fields are right around here near Ketone and...
Well, there are some on the other side. There are some along this row of peaks to out
further
here.
back. Okay.
Yeah, if you see from the air, you'll see more, but you don't see from the road.
So this is a stunning example here. It's certainly one to see. Another feature that you see going up the road, and it'll probably stand out better going down, is there are joints running through the mountain. So these are expansion or exfoliation style joints where you have onion skin sheet layering. The result, of course, of these being plutonic bodies and overburden being removed away, and that unloading causes, of course, stress to pop these things open. And they make nice features. We'll see them also at the Lake Elmer Thomas Dam, so they're pretty stunning. The rock itself, it's highly weathered here on top. This is not the best place to look at fresh granites by a long shot. There are some places where they blasted through along the road, but you can see it's a brick red, orangish red rock. One of the distinctive features of the Mount Scott, and I'll say this many times today, is the presence of these round, gray, ovoid-shaped feldspars. And we've actually decided that's the characteristic that makes the Mount Scott the Mount Scott. So this was pointed out in Clifford A. Merritt's paper back in 1965, which came right after the Ham, Dennison, and Merritt study, so I'm sure he used a lot of the data from that to sort of codify what was going on here. This granite is not that dissimilar from the other Wichita granites. They're all about the same color. They have similar textures. If you look at it hard, you'll see that there's a granophyric ground mass. In the Mount Scott, that varies. It can be more hypidiomorphic in places, but generally where you see it, you'll see this granophyric intergrowth. For those who aren't petrologists, that's the intergrowth of feldspar and quartz coming together. Makes it look almost, like it's not a granite at all. And initially, when things were mapped out here, they were all mapped as granophyres because it wasn't clear exactly what they were. Tim told me a great story last night that he was out mapping Valley Mountain when he was working on his thesis. And the thinking prior to looking at that section out there is that these were all intrusives, that there were no rhyolites out here. So that really is the first step to realize, oh, we're dealing with a complete package here. We got the stuff that's on the surface and the stuff that's underground. But we see lots and lots of this type of granite out here. These are sheet granites, and the geometry of that is somewhat manifested in the contact geometries. But really walking around and mapping this out, you get the feeling that they're laterally extensive, but not particularly deep. So they're coming up into a high level of the crust and basically lifting the overburden. I like to think of them as they're just like the rhyolites, except the rhyolites are lifting the air out of the way, which is no big trick. It's only 14 pounds. And the granites are lifting the rock, which is basically the rhyolite cover. The granites are exploiting an unconformable surface between the Glen Mountains layered complex, which again is this troctolitic, anorthositic, olivine gabbro body with a nice layer similar to Stillwater or the Skiergård or those kind of layered intrusive bodies. And it's clearly a deeper crustal phenomenon. You can't get that kind of structure, in the near surface of the earth. That becomes uplifted and eroded off. The rhyolites cover that, and then these granites come in to that horizon largely, and they largely stick to that horizon.
Why can't it just be a single igneous complex, mafic at the bottom and felsic at the top?
So you want to generate a giant, an orthositic body at 2 kilometers depth.
Underlain by stuff that's it's less than north acidic. but
less north acidic.
And then the
I
granite,
would hazard
Sort of a-
that
sort of a
that would
bush
be
veld
a
or
lot of heat in the neighborhood. That would do a lot for whatever is here. But I don't know if anybody else wants to speak to that. It seems to me that it's more consistent with the GMLC being much more deep-seated, and the dating is not really great on the GMLC unless somebody's done something new that I don't know about. But
We're going to.
okay, so the GMLC, the dating on it isn't really great, but it dates out older than anything else we see, the rhyolites and the granites here.
When was it first realized that it is a layered granite?
The granites are sheet-like. I don't know. Tim, do you know when
time someone looked
people
at Mount
started
Sheridan.
talking about these as tabular bodies?
Or Charles?
Well, I think all the way along this project you could see the sheet-like character of it, and it had been originally interpreted by some people as a lapillet, with it differentiated with the silicic rocks on top and the gabbro on the bottom.
that was Warren Hamilton's.
Yeah, that's Warren Hamilton.
1954.
Okay.
But the chemistry of the mafic rocks is truncated. It doesn't move right up nicely into the.
Oh, that's a good point.
Yeah, it's
Stuff
truncated.
with it.
So there's clearly something different going on.
It's rotated, right?
And you can see the unconformity in places. That's the point. You can see the contacts. There are igneous contacts between granites and gabbros.
And
That's
so
true.
do you see the rhyolite ever on the...
GMLC, you do out.
Not well. We'll have to go back to Dennis and Merritt. They do that on the
yeah.
basis of well cores, basically.
Okay.
In the subsurface.
In the
Yeah.
subsurface, okay.
Well, the contact is sharp then.
Between the
You can see it over on Mount Sheridan.
Yeah.
That's the Roosevelt gabbro. That's the hydric gabbro underneath the Mount Scott. But where you see the gabbro in contact with the granite, it's sharp and pretty horizontal.
Yeah, out further west, but there's rhyolites that are stoked.
I mean, one of the tensions is Charlie says there's an unconformity between the gabbro. I've never
Whatever
seen it,
they
but I
are,
can't-
there's rhyolite in the
I
middle of the
can't
granite.
I can't walk it.
But Bob's point is well taken. Basically, you can view the whole area as mafic on the bottom and felsic on top. It is
The
layered.
problem with what Bob's saying is you're looking at the middle part of the layered complex when you're in the Glen
That's
Mountains.
right.
If you compare these to well-characterized layered complexes worldwide, you're getting this interlayering of north acidic gabbro and troctolite. And you usually get that in the middle parts of these complexes, above the ultramafics, below gabbros, grading up into ferrogabbros, ferrodiorites. You see this whole progression, iron enrichment. And then at the top, you can sometimes get substantial felsic magma bodies, but there's a continuous gradation. And that's completely truncated, where you have Mount Scott resting right on top of the middle part of the layered series with the anorthosites and the troctolites.
And as you say, we don't really have an age yet, right? And the...
Not a good one. We have a Samarian internal mineral isochron of 528 plus or minus 29. I'm not too hip on isochrons, and plus or minus 29 means just can't do anything with it, the kind of timing we're trying to get here.
It's the same age within analytical error,
Yes.
which is the wrong answer.
But it's a huge analytical error.
It's the
yes,
wrong
yes,
answer.
Yes, I understand.
So, continuing onward with the view. Let's continue on with the view. We're going to look at the GMLC at Burford Lake, so we can continue this discussion on where we are in the GMLC at that point. And if you determine where we are in the
Glen Lake.
GMLC, I think that would be news, wouldn't
Glen
it?
Mountain layered.
Are we still undetermined what the
Anhydrous
central
and
lowlands,
orthositic gabbro.
what part of the
Roosevelt
GMLC that is?
gabbros.
Yeah, I mean, it's, some people call it N zone, but the point is it really hasn't been correlated that well outside.
Okay, so I will leave us to argue that point later. I think I was mentioning the granite itself, its characteristics. The other characteristic you'll find in the granite is these enclaves of mafic blobs. They're just clusters of crystals, mostly hornblende and biotite, some accessories as well that dominate over the feldspar concentration. They're all over the place out here, and they're homogeneously distributed. Richard and I were talking about this earlier. The neat thing about this granite body, particularly now if you just map it out as the granite body that contains the ovoid feldspars is that aside from some variations in composition near the edges, it's homogeneous from end to end. And I'll point towards the other end, but you can't see it from here. Richard wants to call this a flood granite as a consequence of that. But really it starts over by Love's and it goes on for 55 kilometers that way. It's broken up, it's not continuous all that way, but there's about 25 kilometers of continuous exposure where you're in the same ovoid bearing granite that has identical composition, almost down to every trace element we could talk about. So very homogeneous mixed material. There, of course, is the problem if you want to argue about something of how you get all this homogeneous stuff to distribute in the crust. Such a wide distribution. Do you have to have multiple vents? Is it just one vent? I don't know the answer to that, but certainly it's a curiosity that we have such a homogeneous unit. It's also the best exposed of any of the Wichita granites, so it's a great place to sort of examine the problems that are all associated with the different tabular bodies. All right, the view. Looking off to the east into the sun, but we got some beautiful reflection off the clouds there. You start sort of to the northeast with the Mears Valley here. The Mears Valley is basically the upper Mears is drained by Medicine Creek. Medicine Creek comes down in front of the mountain here. They've dammed it up for the reservoir. This is the City of Lawton drinking water reservoir. Lake Latonka in the foreground. But you can see that the creek would have ran through right there, and the dam is behind this boulder and that cedar tree, juniper tree that's right in front of it. The rocks in the foreground, the mountains in the foreground, these rocky knobs,